them faster. Okay, so now Fy means that this is fixed, and I'm differentiating with respect to y. When I differentiate this with respect to y, I only get x squared. When I differentiate this with respect to y, I get 6y plus. When I differentiate this with respect to y, I get 8x cubed y. So this is done. Now I want to differentiate again for the second order partial derivative, fyy. Can anyone just help, try to help? It's okay. If you have any difficulties, I'll help you. So we want to differentiate this with respect to y again, knowing that this is fixed.
Wouldn't the first term just be 0?
Exactly. Very good. Now let's differentiate this with respect to y.
6.
That's it. Plus. This stays. I'm differentiating with respect to y. What do I get?
8x to the third.
That's it. Done. Finally, remember a few minutes ago we determined fxy. Now I want to determine fyx. Fy, and then differentiated with respect to x. So, when I differentiate this with respect to x, what do I get?
2x.
That's it. When I differentiate this with respect to x, what do I get?
0.
Perfect. When I differentiate this with respect to x,
24
x squared,
y.
that's it. So now let's choose any other problem you would like to work on. Anything, because I would like to look at the max min. And then we'll come back to more word problems or anything else you would like to determine. Okay, so let's look at something with log, because they look slightly more difficult. So let's look at 15. Feel free to choose 15 on 540. So f of xy equals x natural log of xy. Let's see what they want. They want fx and fy, just fx and fy. They don't want anything else. I'm happy. It's not going to look ugly. It's going to look ugly. It's not going to be an easy situation. But they only want for this function, and they only want from us fx and fy. Good. So for fx, we know that this is the partial derivative with respect to x. And that means that this is a function of more than one variable. And we have it right there. So when I differentiate with respect to x, this will be considered fixed. Function 1, ugly. Function 2, and then inside, it's not a big deal because y is fixed. But I still have to use the product rule. First function times the second function. So the first function prime, how much?
1.
Yes. So times natural log of xy. Very good. Plus x times natural log of xy where y is fixed. Prime. When I differentiate natural log, what do I get?
1 over x.
Very good. 1 over xy times the inner function prime. I'm differentiating this with respect to x as if y is 15 or 20 or negative 3.
Times y.
Excellent. Look what happens. Really nice. These two go away. One from the top, one from the bottom. These two go away. One from the top, one from the bottom. So the answer is natural log xy plus how much?
1.
Thank you very much. Awesome. Good. So for the same function, we want to determine fy. I'm going to copy the function here, sorry. I just want to put this away. So x natural log xy. Okay, so when we are differentiating with respect to y, this is fixed. So now I do not have to use the product rule, because this is a constant of natural log of a constant times y. So this is easier, right? So fy equals constant stays in front times natural log is 1 over xy, and we are differentiating with respect to y. So when I differentiate this with respect to y, I get x. So these two go away, so the answer is x over y. So one here and one here. Would you like to choose anything else before we look at max min? And we'll come back to more problems here, word problems.
What numbers can we choose from?
Anything you like from 1 through 40, and then we'll come back to word problems.
Okay, can we try 36?
36 it is. 36, I see it. So fxy, f of x and y, is e raised to xy, and they're asking us to determine everything. fxx, fxy, fyx, and fyy. So we can never get to fxx, fyy, fxy before we find fx, before we find fy. We can never determine these without the first partial derivatives. Okay, perfect. So let's start. fxx. So this is when we did differentiate with respect to x when y is fixed. Okay, so this is e to a function. E to a function prime is e to that function times the function prime. But y is fixed. So when I differentiate with respect to x, assuming y is 15, what do I multiply by? Excellent. Excellent. Good. Same thing. It has to be the same, because now x is fixed. So I have e to xy, but since x is fixed and I differentiate with respect to y, I get x. By symmetry. Okay. Now we can address this. So fxx means it's a constant because y is fixed. I differentiate with respect to x. Y stays outside, but I differentiate this with respect to x, which we already know it's e to xy times xy prime with respect to x, that will be y. So this times this will be y squared. So this is done. Okay, now I can differentiate also fxy. I can find fxy. I have fx and I have to differentiate with respect to y. But now, so I'm differentiating this function with respect to y, which means that this is a function, number 1, and this is another function, number 2. I have to use the product rule, because I'm differentiating with respect to y, and y is in both. This is the variable, and this is fixed. So I differentiate the first one, e to a function times the function prime. I'm differentiating with respect to y, so this is x, times the second function, plus e to xy times y prime, that is 1. I could factor out e to xy and get xy plus 1. So this is done. In a moment we will also add to it fyx to check that it equals fxy. Okay, so now we do have fy, so let's also find this before we find fyy. So fyx. So we're differentiating this function now with respect to x. So, moving on, 6. I'm going to copy it here. Fy equals x e to xy. And now we want fyx. So now I have to use the product rule. I'm differentiating this function with respect to x. So this is function 1, and this is function 2. First function prime is 1. So e to xy plus the first function times the second function with respect to x, right? E to xy times this with respect to x is just y. I will factor out e to xy, and I have 1 plus xy. I'm going to write it like this so everyone sees that it's exactly the same. So that was done. We still have fyy. So this fyy. Okay. So now if I differentiate with respect to y, this is a constant. This is not the product rule now. X times e to a function, e to xy, and I differentiate with respect to y, and I get x. So this will be x squared e to xy. Interesting problem. Thank you for choosing that one. Anyone else would like to choose, or can we look at the max min and we'll come back? I want to share my screen for a second to show you. Look how nice the book works now. I could not, months ago, I could not bring it up. So what I would like to explain here is, what is this partial derivative? What is this partial derivative when, for example, for fy, when x is fixed? Well, this is a surface, right? When we talk about 3 variables, f is the function, right? Or z. Z is one variable, x is another variable, and y is another variable. We get this three-dimensional surfaces. So the function, that weird function that I chose, it's a 3-dimensional surface. So when we keep fixed one of the variables, we will get this plane, the blue plane that you see here. When we keep one of the variables fixed, we get this blue plane. And the derivative fy, fy, which is the function differentiated with respect to y when x is fixed, or the other variable is fixed, one of the 3, one of the 2, because z is the function, then it gives us the slope of this line. So this is when we calculate d function over dy, or fy, the partial derivative fy, that's all we get. We get the slope of such a line. The other thing I was going to show you, because I like to explain max min, I love it. I think they fixed the problem. I think you said, some of you said that it's not fixed, but for me, for some reason, it's fixed. Look at these surfaces, 3-dimensional surfaces, right? The function is z, x is one variable, y is another variable. They all, the ones in the picture, have a max or a min. See? There is a max here. There is a min here. And there are other very nice pictures. Okay? So here is an absolute max. Here's a relative max. Here's a relative min, or an absolute, and also an absolute min. Very nice pictures. I really like them. Okay? Now, here, this surface does not have a max or a min. It has something called a saddle point. Right? Like you sit on a saddle on a horse. So that's why the name of the saddle point. No max, no min. So we're going to talk about the same thing here. We're going to talk about what is called the d-test. The d-test will ask us to determine because we are trying to determine the max min of such a surface. Max, min, relative max, absolute whatever, right? So in order to determine for such a surface, if it has a maximum or a minimum, look at the calculations. This is open book, right? You're going to have this in front of you. So it's called a d-test. So we have to determine fx, fy, fxx, fyy. First order partial derivatives, second order partial derivatives, and the combined fxy or fyx. We know that they're the same. We have to solve a system of two linear equations, or equations, they don't have to be linear. fx0 and fy0. Like we did before with the critical numbers. Same idea, right? We set the derivative set equal to 0. But now we have two partial derivatives, fx and fy, set equal to 0. And we determine a point, or maybe more. And we evaluate what is called the d-test, right? We evaluate this for both, or three of them, or just one of them. After we determine the value, we have these options. If d is 0, the test is not applicable. If d is less than 0, there is a saddle point right here. So it does not have a max min. But if d is positive, there are two options. A minimum and a maximum. A minimum when fxx evaluated at that point is positive, that's a minimum. And when fxx evaluated at that point that we determined in part 2 is less than 0, then it will be a maximum. That's what I want to do for the next half an hour or so. Okay, I'll stop sharing now. So let's talk about, so this is the last section, 6.3, max min for functions of two variables. Okay. So let's choose an example. Anything you'd like to choose on page 547. Page 547, anything you'd like to choose from 1 through 14 to discuss the d-test to find the max min of a function of two variables. 6 it is, very good. So we have for f of x comma y, we are given for 6, x cubed plus y cubed. Minus 3xy, very good. And find the relative max min values. Okay, so we're going through step by step to compute everything we need for the d-test. In step number 1, I have to determine fx. Can anyone give it a shot for fx? It's okay if you're wrong.
3x